Hey there, good evening. I am Anurag Singh, a third year undergraduate student at the Indian Institute of Technology, Kharagpur. I am currently enrolled in AlgoZenith's AZ201 batch number B07. This is an explanation video meant to be submitted for the AlgoZenith's internal hackathon. In this video, I am gonna be explaining the entire journey which I went through for building my project app GoAlgo. Now, before I begin, I just want to make a small request. Please watch the entire video to get the complete overview of my journey for building this app. Okay, so without further ado, let me begin. So first things first, what actually is GoAlgo? GoAlgo is a search engine that is nothing but a software system designed to carry out searches. It scans its corpus consisting of a whopping 6,500 plus documents in a systematic way for particular information specified in a textual web search query. The top 5 results are presented in a line of results referred to as search engine result pages, as there in any other search engine, just like Google or Bing or etc. Notably, GoAlgo is a vertical search engine. Now, what do I mean by a vertical search engine? Vertical search or specialized search is a way of narrowing your search to one topic category rather than the entirety of the web. In the case of GoAlgo, the specific topic it deals with is commonly used data structures and algorithms and problems based upon them. Some other examples of vertical search engines include the search bar on shopping sites like eBay and Amazon, Google Scholar, which indexes scholarly literature across publications, and searchable social media sites and apps like Pinterest. Now, moving on to how GoAlgo works. Using GoAlgo is easy, isn't it? You open up the search page, type a few words into the search bar, and voila! A list of top 5 results appear in mere seconds. But under the hood, a lot of heavy lifting is being done. Search engines out there in the wild are pretty complex when it comes to the algorithms they use. But GoAlgo follows a pretty basic formula. It's a simple two-step process. Let me explain you. The step 1 is a search. When you enter your query, GoAlgo must pre-process your words into relevant terms. This is done by a host of natural language processing techniques, which I am gonna be covering later. The output of this initial translation process is a rewritten query that identifies the important parts of your query, which corrects misspellings, lemmatizes the query, converts numbers to their word equivalents, etc. etc. GoAlgo then skims through its corpus to find web pages that match the rewritten query. Moving on to step 2. Step 2 is rank. Now ranking. A single search may turn up thousands of relevant documents in our corpus. So the part of the job of GoAlgo is to sort these listings using some ranking algorithm. And although these algorithms are designed to provide you with the best answers to your questions, they are biased towards certain factors. Now, listening to all this makes one thing clear for sure, that it's all about this scoring function which we are going to use. Now, in order to rank the document, engine use a variety of complex algorithms which take into consideration a plethora of things for ranking documents. However, the algorithms used in the case of GoAlgo is much simpler. Today, I am going to be talking about commonly used calling functions that are tf-idf and bm25. I will briefly talk about each of these two scoring functions and how I implemented them in my own project. Let us start with tf-idf first. Let's review tf-idf by trying to develop it from scratch. Assume we have already got a way to find the documents that match a user's search. What we need now is the ranking function that will tell us how to order these documents. The higher a document score according to this function, the higher up we'll place it in the results that we return to the user. The goal of tf-idf and similar ranking functions is to reward relevance. Say a user searches for the term dogs. If document 1 is more relevant to the subject of dogs than document 2, then we want the score of document 1 to be higher than the score of document 2. So we will show the better result first and the user will be happy. How much higher does document 1 score have to be? It doesn't really matter as long as the score order matches the relevance order. We'll make a simple but profoundly helpful assumption. We'll assume that the more times a document contains a term, the more likely it is to be about that term. That's to say, we will use a term frequency, that is TF, the number of occurrences of a term in a document as a proxy for relevance. This one assumption creates a path for us to solve a seemingly impossible problem using simple math. Our assumption isn't perfect and it goes very wrong sometimes, but it works often enough to be useful. So from here on, we will view term frequency as a good thing, a thing which we want to reward. Now let us move to the step 1 of building the tf-idf algorithm. As a starting point for our ranking function, let's do the simplest, easiest thing possible. We'll set the score of a document equal to its term frequency, as simple as that. If we are searching for a term T, let's say, and evaluating the relevance of document D, then the score of dt would be term frequency of dt, respectively. When a query has multiple terms like dogs and cats, then how should we handle that? Should we try to analyze the relationship between the various terms and then blend the per term scores together in a complex way? Not so fast, isn't it? The simplest approach is to just add the scores for each term together. So we will do that for now and hope for the best. If we have a multi-term query Q, let's say, then we will set the score of dq equal to sum of all terms t in Q of score dt. That is the sum of all individual scores of the terms involved in a query. Now, how well does our simple ranking function work till now? Unfortunately, it has got some various problems. First problem is longer documents are given an unfair advantage over shorter ones because they have more space to include more occurrences of a term, even though they might not be more relevant to the term. Let's ignore this problem for now. The second problem is all terms in a query are treated equally with no consideration for which ones are more meaningful or more important. When we sum the scores for each term together, insignificant terms like and the, which happen to be very frequent and will dominate the combined score. Say you search for elephants and cows. Perhaps there's a single document in an index that includes all three terms, elephants and cows. But instead of seeing this ideal result first, you see the document that has the most occurrences of and. Maybe it has 10,000 of them, 10,000 of the stop word and I'm talking about. So this preference for filler words or stop words is clearly not what we want. So let us move to a step further. To prevent filler words from dominating, we need some way of judging the importance of the terms in a query. Since we can't encode an understanding of natural language into our storing function, we will try to find a proxy for importance. Our best bet here is rarity. If a term doesn't occur in most documents in the corpus, then whenever it does occur, we will guess that this occurrence is significant. On the other hand, if term occurs in most of the documents in our corpus, then the presence of that term in any particular document will lose its value as an indicator of relevance. So high term frequency is a good thing, but its goodness is offset by high document frequency or DF, the number of documents that contain the term, which we will think of as a bad thing. To update our function in a way that rewards term frequency but penalizes document frequency, we should try dividing TF by TF. So the score for a document D for a term T would be term frequency of dt divided by document frequency of the term T. Again, what's wrong with this? Unfortunately, df by itself tells us nothing. If df for the term elephant is 100, let's say, then is elephant a rare term or a common term? It depends on the size of the corpus, right? If the corpus contains 100 documents, elephants is common. If it contains 100,000 documents, then for sure elephant is rare. So let us move on a step further. Instead of looking df by itself, let us take a look at n by df, where n is the size of the search index or corpus. Notice how n by df is low for common terms. 100 occurrences of elephants in a corpus size of 100 would give us an n by df of 1, and n by df is higher for rare occurrences. Like for example, if elephant is rare, let's say it occurs 100 times for a corpus of size 100,000, n by df would be 1000. That's exactly what we want. Matches for common terms should get low scores. Matches for rare terms should get high ones. So now our improved formula looks like score of a document for a term t equals to the product of term frequency into n upon document frequency. We are doing better, isn't it? But let's take a closer look at how n by df behaves. Say we have 100 documents and elephant occurs in one of them while giraffe occurs in two of them. Both terms are similarly rare, but elephant's n by df value would come out to be 100 and giraffe's would be half of that at 50. Should a match for giraffe get half the score of match for elephant just because giraffe's document frequency is one higher than elephant's? The penalty for one additional occurrence of the word in the corpus seems too high. Arguably, if we have 100 documents, it shouldn't make much difference whether the terms df is 1, 2, 3 or 4. So let us move to the final step. As we have seen, when df is in a very low range, small differences in df can have dramatic impact on n by df and hence on the score. We might like to smooth out the decline of n by df when df is in the lowest end of its range. One way to achieve this is to take the log of n by df, which the tf-idf algorithm takes as well. If we wanted, we could try to use a smoothing function here, but log is straightforward and it does what we want. Okay, so now let's call n by df the inverse frequency of the document, or idf, log of n by df, I'm sorry, log of n by df, let's call it inverse document frequency or idf of a term. Now our ranking function can be expressed as score is equal to product of term frequency and inverse document frequency. Henceforth, we have arrived at the traditional definition of tf-idf, and even though we made some bold assumptions to get over here, the function works pretty well in practice. It has gathered a long track record of successful application in search engines. So, are we done here, or could we do even better? Okay, so the answer is yes. Now that we have talked about tf-idf, let's quickly discuss BM25 as well, which can be seen as an improvement of tf-idf. Unlike tf-idf, in BM25, not two but three or more factors affect the weight of each query term. Two of which we have already seen earlier are tf and idf respectively. BN25 goes beyond these two factors and takes into consideration a third factor, that is the length of the document. One may ask why. Let me explain you why. Because a million-word document will mention all query words but may not actually be about the query. Instead, a shorter document that mentions all the words is a much better candidate. This is the notion behind BM25. Okay, so now let us briefly have a look at the formula of BM25. I have it over here in my snipping tool. So as you can see, what I have in front of me is the formula of BM25 scoring algorithm. So BM25 score for a document DJ against the query words Q1 to N, Q1 to N is calculated using this formula. Here tf-qi-dj is the count of number of times word qi appears in a document dj. Modulus of dj is the length of the document d in words. L is the average document length in the corpus. K and B over here are some parameters that can be tuned by cross-validation. IDF of QI is the inverse document frequency of the word in the query QI. DF of QI gives the number of documents that contains the word QI. Okay, now n over here in this n in the IDF equation is the total number of documents in the corpus, and n in the BM25 equation overall over here is the number of terms in the query, that is the number of words that a query is composed of. So in a nutshell, BM25 goes beyond tf-idf to account for document length and term frequency saturation. So this was all about the scoring functions. Now that we know all about scoring functions, let me take you to a walkthrough of my corpus and the implementation of scoring functions in code. Let us first quickly take a glance at the corpus. So here I have opened the SQLite database which my code is using, which serves as the corpus for my project. So as you can see over here, there are various fields that are ID, title, keywords, URL, and HTML. So for example, we have a question or a problem on any website. For here, I have scraped using various websites. Let's say the first question, as I know, has been scraped from SPOJ. So let us consider this example. It has an ID of 1. Atul and Astha Chronicles is the title of the problem. Then I have keywords mentioned in this entire problem. I have extracted these keywords after doing some pre-processing. I have a relevant URL regarding the problem, and this is very interesting. I have also stored the relevant HTML code regarding the particular document. Now I will come to this later, but the brief notion behind doing this thing is that I cannot make I cannot maintain, as you can see over here, 6651 fields are there. I cannot maintain 6650 on separate HTML pages, right? So the approach that I followed was I stored the relevant part of the code which is to be displayed on the individual page of the problem. Okay, and I serve this from the database itself. So when the time comes for displaying an individual problem on the web page, I just have one boilerplate code in which I insert the relevant HTML code corresponding to each of the problems. So that reduces this entire task into a minuscule task of just having one page which has some boilerplate and inserting the HTML code from the database itself. Interesting, isn't it? Okay, so now that we have seen the corpus, you can see over here there are a lot of data fields which I have extracted from various websites. Yes, you can see our interview bit is there. I have also scraped from some from Geeks for Geeks, and I have from Lead Code as well. Let me scroll up. Yeah, so these are Lead Code. So these are the 4 websites which I have used for scraping my questions, and the corpus size is over 6500 documents, which is pretty huge in itself. Now that we have had a look at the corpus, let us move on to have a look at the code. I have the code opened in my text editor. Okay, so let me begin the walkthrough with this file. Yeah, the logic.py file. Why so? Because the logic.py file contains all the logic and implementation needed to run the search engine, as its name itself suggests. Okay, now let us have a walkthrough at this logic.py file. Let me begin with the implementation of tf-idf, as the implementation of BM25 in code is much simpler compared to this. So over here you can see all I have is the necessary imports required to run the engine. I have imported them over here. Okay, Here I am making the connection to my database and making a pandas data frame. The pandas data frame has similar fields as we had in the corpus, that are title, keywords, URL, and HTML. So beneath this, I have four major functions for implementing tf-idf. Out of this, one function will be used for BM25 as well, which is the pre-process one. So these four major functions are this pre-process, which pre-processes the input, as simple as that sounds. Next one is create tf-idf features. What this method does is creates tf-idf matrix for the corpus using scikit-learn. Next method we have over here is calculate similarity method, which vectorizes the query via tf-idf vectorizer, which is inbuilt in scikit-learn, and calculates the cosine similarity. Yeah, cosine similarity of the query with X. What is X over here? X is all the documents. So basically we calculate the cosine similarity of the query against all the documents and return the top k documents. As you can see over here, top k is given as a parameter. I have set it to 5 as that was the requirement. I will be returning top 5 queries. Okay. Next method that we have is show similar documents. This method does nothing but prints the most similar documents using indices in the similar doc indices vector. Okay, one thing which I forgot to point out is that I have sneaked into the basically the ID of the problem -1 into keyword section over here like this, so that when I get the keywords, when I get the document, relevant document being returned, I can just extract its ID by splitting it from white space and extracting the first one. And after that, I can use that to index the pandas data frame and return the relevant title as well as the URL, etc., etc., things related to that particular document. Okay, below this, I have the logic for BM25 on which I will be coming over later. So now that we have seen all the methods, it's time for some action, isn't it? Now let us see all this in action in a stepwise manner. For this, let me move on to app.py. So again, here I have some basic imports. Since mine application is a Flask application, these are some imports related to Flask and Beautiful Soup. From logic, I have implemented the necessary methods, and here is a form, main form, which I will be using for search. This example is basically my database structure, and I have some routes, the home route, search route, which has a dynamic search functionality depending on what is being typed. Okay, so most of the work will be done in this one, in this thing over here. So let us start. Let us try to have a look at how things work. Okay, so since I will be talking about tf-idf first, I had talked about tf-idf first, pardon me. I will show you the working of tf-idf code first. Then we will come to BM25. Okay, so I will be commenting the part of BM25 and using tf-idf instead. Okay, so I think I have commented all the things related to PM25. Okay, this research function and all that also I think I should comment, since these are related to BM25 and come in a further version of me of my project. So I am commenting this research as well. Give research options and all. We don't need. We just need to see the tf-idf scores. These routes are not needed for now. Let us just see this much in action. So in order to run it locally, I am in the directory, as you can see over here, GoAlgo version 1 local directory, and it seems like I already had activated my virtual environment, so let me do it again for you. Okay, my virtual environment has been activated. Now let me run the app. Hope it works fine. Okay, so it is running over this URL. Uh, this is the local URL. Let me refresh the page. Yeah, so we are on the page. Now let us try to search for something. So yeah, I have searched for binary tree, and as you can see over here, we have got the top 5 results as expected. But the thing is, these are the 5 results returned from the tf-idf. Let us have a look at the console. Yeah, so as you can see over here, we have the binary tree. That's our query. Spelling and all seems correct. This is the query that I print after pre-processing for my own purpose. Now here is the tf-idf matrix was created, and then we can see over here the top 5 tf-idf results with their similarity scores respectively. So as you can see, the scores are quite relevant, right? And the results returned are also quite relevant. tf-idf seems to be working fine. Now let us take a step-by-step look at what's happening inside the code. Let us have a look at the first method, preprocess. Now, pre-processing is one of the major steps when we are dealing with any kind of text method models. As you can see, the body of the question, it's true for all questions, may have special characters or let's say different cases. Okay, the pre-process function will do nothing but carry out the cleaning of the query text by removing HTML tags or any such special characters or digits. As usual, I have also improved upon this by including something like word to numeric functionality. I have also used WordNet lematizer for lemmatizing the search query. I have also removed the stop words so that I only search for relevant things. So these all things are being done in the pre-process method. After we load and clean the data, next we create the term document matrix. As you can see, the console printed that. Yeah, matrix creation. So it's time for creation of term document matrix. We can write simple functions for computing tf-idf. However, I implemented this and it turned out to be a tedious process. To make the code more cleaner and implementation a little bit simpler, I am using scikit-learn tf-idf vectorizer to compute the word counts, tf-idf, and idf values all at once using the built-in tf-idf vectorizer method of scikit-learn. Please note, I restrict the maximum features to 5000 to make the computations a little bit cheaper and hence make the working of the entire engine a little bit faster. Once they have been done, we print this thing, creating tf-idf matrix and created successfully. Now it's time to test and see how our application works, which we have already done. We asked an arbitrary question over here, that is binary tree. We ran the query. and we waited for the results to come. So as you can see, the results came. Reading the corpus, done, calculating the scores and all that. Right. Here are the top 5 results returned as well. Let's try on some another query. Let's say any random query. I cannot think of anything. Okay, graph. So we get some relevant questions related to graph, right? So this was all about the implementation of tf-idf's code. Now let me revert and come to the implementation of BM25, which is very simple as compared to what we did for tf-idf. Why is it simpler? Because for the implementation of BM25, I have used rank BM25 package for the for implementing it, as it is very fast and returns relevant results in a jiffy. As you can see over here, I have imported BM25 Okapi from rank BM25 package. Now let us see BM25 work in action. For that, I will just uncomment all these things which are relevant to BM25 and comment all these things which were relevant to tf-idf. Okay, seems like everything related to BM25 has been done. Now let us have a look at the terminal and try running some queries. Again, we come over here. Let us type something binary tree. Yeah, so as you can notice, the match score have been changed as the scoring for BM25 and tf-idf works a little bit differently. Also, you can see the results have also been changed. If you look closely, you can see this set of results seem to be a little bit better than the previous one. Why? Because we can see the occurrence of binary tree right itself in the title as well. And even as the internal functioning of BF25 works, it is slightly better, not slightly, definitely better than TF-IDF. So as it seems to be working fine, this is what we obtained as our results. Okay. So now that I have walked you through all the code, I would like to take the opportunity to speak a little bit on my thought process while building this project. Also, I will be walking you through the remaining code as well. So yeah, just on a note, I forgot to tell you about this run BM25 function. It does nothing but it uses the preprocess function, preprocesses the query, and runs BM25 function, built-in function over it to return the top 5 results. Yeah, so as I was talking, let me talk you through the thought process which I have gone through while building this project. Definitely, the 4 factors which I took into consideration while building this project was the first factor is correctness or accuracy. Okay, now this factor is the sole reason for which I have preferred BM25 over TF-IDF in my final version, final hosted version which I am talking about over here, right? Even though I have implemented the code for both, as you can see over here in the logic.py file, I have the relevant code for both BM25 as well as TF-IDF. But I ran some sample searches and found the results yielded by BM25 to be better overall. That's the only reason that I have preferred BM25 over TF-IDF in my implementation, even though I have both the code.